This is a walkthrough of Section 2 of Chapter 1 in the book Problem Solving with Differential and Integral Calculus. Section 2, the circumference of a circle. There's a circle, radius r. The circumference is the distance around the perimeter of the circle. The normal equation that relates the circumference c to its radius r is c equals 2 pi r. Pi is 3.14159, etc. Just some constant. So a swimming pool that has a 10-foot radius will have a circumference of about 63 feet. This relationship is linear. C versus r is a straight line. We can plot it. This is the normal equation. C equals 2 pi r. And this is a map of the circumference for any radius. So we can put a dot at 10 centimeter radius. That's a radius of 10 centimeters, and we can look across to the y-axis to see that the circumference is about 63 centimeters. If we can go over to 18 centimeters, put a dot there, that's 18 centimeters. We go horizontally over to the y-axis, the circumference is about 113 centimeters. So now we're going to switch gears and focus on differences. So the difference in the radii from 10 to 18 is 8 centimeters. The difference in the circumference from 63 to 113 is about 50 centimeters. So the question is, if the radii of two circles are different by delta r, what is the difference in their circumferences? Delta c. What's the relationship? What's the difference equation? We can calculate it using the normal equation. So we'll consider two different circles. One has radius r1, circumference c1. One has radius 2, circumference c2. The equation for the circumference of the circle is the same for any circle. C is 2 pi r. So we can write c1 is 2 pi r1, c2 is 2 pi r2. The difference is delta c is c2 minus 1. The difference in the radii, delta r, is r2 minus r1. So let's subtract the circumferences to get delta c. Delta c is c2 minus c1, which is 2 pi r2 minus 2 pi r1. We can factor out the 2 pi from the right-hand side and write the difference in the radii, r2 minus r1, that's delta r. So the difference equation is delta c is 2 pi delta r for any two circles. Now let's look at the slope of the line. Slope of the line is the rise over the run. The rise is delta c. The run is delta r. It's a straight line. We can take any delta c and delta r that we want on the line. The difference equation is delta c is 2 pi delta r, and you can see there's a delta c and a delta r in there. If we divide both sides by delta r, we get the slope. The slope is 2 pi everywhere. It's a straight line. So it's interesting to note that the difference equation is not a function of the radius of either circle. R2 and R1 do not appear in the equation. Delta c is 2 pi delta r. It doesn't matter what the radii are, only the difference. So we can look at the Earth and the Moon. The difference in their radii is 4638 kilometers, and from that alone, we can calculate the difference in their circumferences. Delta c is 2 pi delta r. The difference in their circumferences is about 29,000 kilometers. There's a nice problem in the textbook, the rope around the Earth. You put a rope around the Earth tightly, so its circumference of the rope is the same as the circumference of the Earth. Then you add 1 meter to the rope, raise it a distance above the Earth, and calculate that distance. Interesting problem. So there's the Earth, and exaggerating, there's a rope around the Earth. Nice problem. So here are the takeaways from section 1.2. The difference equation for a circle relates the differences in the radii and the differences in their circumferences. And we can get the equation from the normal equation, c equals 2 pi r. So we recommend to test your mastery of this concept, to really wrap your head around difference equations. There's a number of exercises and problems at the end of section 1.2 in the textbook. Get to work.